Okay, this is part one of the 9.3 section, geometric sequences and series. Should take about 5 parts on this one. It's just like it did on the arithmetic sequences and series. And I begin this section with the definition of what a geometric sequence is. And it says a geometric sequence is a sequence where there is a common ratio between consecutive terms. So if you recall, on the arithmetic sequence, there's a common difference between, so there's a gap, yet you add the same number every time. Well, in geometric sequences, since it's a common ratio, you're basically multiplying by the same number every single time. So the ratio is found by dividing consecutive terms. So on this one, for example, example 1, the sequence is 1, 3, 9, 27, 81. So if you multiply 1 times 3, you'll get the second term. If you get 3 and you multiply it by 3, you'll get the next term. By 3, and then by 3. So the ratio between the terms is 3. And how you figure that out is just divide any two consecutive terms, and maybe it's the third term by the second term. If you prefer, it could be the second term by the first term. It doesn't really matter. And so it's going to be 9 divided by 3, which of course is my 3. So this is definitely a geometric sequence. So there's a common ratio between the terms. Now that's when it's a nice, kind of nice number. And but look at example 2. The first number in the sequence is 48, and the next one is negative 24, and the next one is 12, and the next one is negative 6, and the next one is positive 3. And so when you go from 48 to negative 24, if you multiply by negative 1/2, you'll get that. And if you multiply negative 24 by negative 1/2, you get a positive 12. And if you multiply positive 12 times negative 1/2, you get negative 6. And then negative 6 multiplied by negative 1/2 is 3. Now, the next number in the sequence would not be a nice number, or at least not very nice. You multiply it by negative 1/2, you'll get negative 3/2. And then it goes to positive 3/4, and so on down the line. So, but in this case, r is negative 1/2. But in order to figure that out, if you're just given the sequence, again, you just divide any consecutive term. So you could divide the second term by the first term. So it'd be negative 24 divided by a positive 48. And if you reduce it, yep, it's negative 1/2. So that's what a geometric sequence is. Instead of adding the same number each time, you're multiplying by the same number each time. And just like it was with the arithmetic sequences, why they are important to discuss is because just like those, you can actually find specific terms of a sequence, or you could add the terms up of that kind of a sequence. So just like it was in arithmetic sequences, they just use different formulas. So the formulas that you'll be using here is a sub n equals a sub 1, which is the first term, times r, which is your ratio, times raised to the n minus 1. So again, these formulas are non-negotiable. You got to know them. You can't just half get it right, half get it wrong, because if you get it half wrong, it's all wrong. You can't get it. You can't just get part of it right, because the formula is not going to give you the right numbers if you don't have it correct. The sum of the first n terms, which is a finite sequence, is going to be a sub 1 times 1 minus r to the n over 1 minus r. So this will find the sum of the first n terms. So say, for example, if you are wanting to add up 1 plus 3 plus 9 plus 27 plus 81, and you stop right there, then what you do there is you can use this formula. There's 5 terms in the sequence, 1, 2, 3, 4, 5. So you do s sub 5 equals a sub 1, which is the 1, it's the first term, 1 minus r, which is 3 in this case, to the 5th power over 1 minus 3. And put it in your calculator if you have to. I would do a little bit of preliminary math before I put it in my calculator if it was me. But anyway, you do that and you get the answer. And we'll do some problems like that in a minute. And the sum of an infinite sequence is s equals a sub 1 over 1 minus r. And r has to be between negative 1 and 1. Now this one's going to require a little bit more talking about than what I want to spend time with right now in part 1. This is going to be its own little part later on in this, so it's going to be like part 5. This actually is going to be part 5 that I'll be using this one. And I'm going to save that for last. And but I wanted to put the formula down just to remind you, just all the formulas that we use in 9.3. Now, I will also want to show you, remember back in arithmetic sequences, we had a relationship between the arithmetic sequences and linear functions. If you recall, the slope represented the common difference. So they're kind of like cousins, if you will. Well, I got another set of cousins in this one. Geometric sequences and exponential functions. Instead of linear, these are exponential. And if you look at this, a sub n equals 3 times 2 to the n. If you find the first four terms, the first term is 6 because you plug in 1, 3 times 2. Second term, 3 times 2 squared, 3 times 4 is 12. Third term, 3 times 2 to the third, 2 to the third is 8, times 3 is 24, and then 48. Okay, so if you find the ratio is found by dividing consecutive terms, 12 divided by 6 if you wish, 48 divided by 24 if you wish, or 24 divided by 12. It doesn't really matter which way you go with it. It's still 2 no matter what. Now let's look at that same thing, but look at it from the exponential perspective. F of x equals 3 times 2 to the x. So if you can see the pattern, the same pattern. This is what we would have looked at back in chapter 6. Back in chapter 6. The base here is 2. As a matter of fact, the function kind of looks like this kind of a shape. But one of those characteristics of that exponential function is its base. And the base is 2. That's the same as the common ratio down here. So that is the connection between the exponential functions and the geometric sequences. They have the base on the geometric sequence. If you look at it from the exponential point of view, it's the base on that one. So it's kind of the same idea. So I wrote it down here. Common ratio is the same as the base. So it's kind of nice. Remember back in the 9.2, the arithmetic sequences, anything that looked like a linear function in the sequence, if it was written out in a formula and it was linear in form, then it's arithmetic. And if it's not written in linear form, it's not arithmetic. Same thing applies here. If the equation is written in exponential form, then it's a geometric sequence. So that's how you identify the ones that are geometric and ones that are not geometric. So that's the idea. So that's what they're going to kind of look like. Now, again, these are the formulas that we'll be using for this section. So the next four parts of 9.3, what we're going to be doing on the next 4 parts is to just do different types of problems from the sections. And yes, part 5 will conclude with the infinite series. So stay tuned for part 2.